So the first thing that I want to point out is this might be a confusion about sort of the last time what I said. So there's a difference between a boundary edge and an edge. Okay, so this is sort of something that I've just used as an English word, but so what I meant by a boundary edge is something kind of specific. So recall that when we looked at a Mobius strip. Okay, so let me just try to draw one. I mean, so the one that we made, I guess all of you have now perhaps made. This is what a Mobius strip looked like, and topologically, of course, there is some very neat representation. We just represent it as a rectangle with these sides glued, right? So there was a boundary edge. Remember, we talked about this. So the edge was something like this, right? This went here, and it goes here, and goes there, and goes around, right? And then it comes back, and it connects up, right? There's one boundary edge. And even in this topological picture, you can see this. It goes here. This is connected with this, right? Because these arrows indicate that these edges are identified with a flip, and then it continues here and it goes there, but this is the same as this upper left corner again. So that's your boundary edge. So this is sort of the, well, let me just turn this. So this is the boundary edge that I've marked. Okay, and if you take another surface like with a boundary edge, so a cylinder is a surface with a boundary edge. Okay, so let me try to draw a cylinder. So this boundary edge is something that in the sort of English sense of edge, you're an edge of this. If you cross it, you'll fall off, right? I mean, this is what happens if you're an ant on a cylinder, right? You walk along the cylinder, and then suddenly you find yourself in this sort of sharp kind of edge. Okay, that's what a boundary edge is. So for a cylinder, there are two of these, right? There are two boundary edges. Okay, and the notion of an edge that we sort of talked about in the first session, etc. The usual edge is just an edge in a graph, right? Remember, I was sort of drawing the vertices, and then these edges are these sort of these green lines, right? So these edges in a graph, right? So a boundary is a boundary of a surface, okay, which is a sharp edge that an ant might fall off when it goes, okay, and an edge when you're talking about a graph is just the sort of a straight line, and maybe I wasn't too sort of specific or clear when I talked about the definitions of a closed surface. So has no boundary edge. Okay. Okay. For instance, so these Mobius strip and cylinder are not closed. Okay, because they do have a boundary edge. Okay, but something which is closed. So the example is a sphere. A sphere which looks like this, right? So let me remind you what a sphere looks like. Well, this is closed. It doesn't have any boundary edge, right? And a Klein bottle is closed because, well, okay, so let me try to draw Klein bottle as you might try to kind of, so it self-intersects, right? And it goes inside and then connects up. So the Klein bottle is closed. There are no boundary edges. So when we talk of this classification of surfaces, we actually look at things without boundary edges, okay? And we also, I mean, actually, so closed also sort of also means that it, so it's not only does it have no boundary edges, it's also compact. Okay, so maybe some of you who have been reading more of this book of Armstrong, more of topology, already know what compact is. But otherwise, never mind. The key thing is that this does sort of doesn't have any boundary edge. Okay.
Excuse me, sir.
Yeah.
Torus.
Yeah, torus also has no boundary edge, right? So it is a closed surface. Okay, so that's a torus. There's no. If you're an ant, then all points look the same, and sort of there's no edge to kind of fall off. If you're on a cylinder, as we saw, there is an edge, right? So there are two edges. Okay, so that's a boundary. Okay, so a surface with boundary is something different, okay, than, so usually when one says a surface, one actually means something which is without any boundary, okay? But in any case, we surface with boundary come up in real life. I mean, for example, another surface with boundary is a disk, right? So a disk is not closed, right? It's not a closed surface, right? So not, let me write it fully. So not a closed surface, right? Because it has a boundary. There's a boundary circle, right? So there's a boundary circle. You shouldn't also confuse it with, if you're talking of topology, some of you might have already read about closed sets and open sets, and that comes up in analysis also. This closed is different, okay? This is about surfaces, okay? This is about closed surfaces, meaning it doesn't have any boundary edge and it's compact, okay? There's something to do with surfaces, okay? So sometimes certain words in mathematics get used quite often in different contexts. They might mean different things, okay? So something to keep in mind. All right, so so closed, well, things which are not a closed surface are also kind of equally kind of important, and they arise, like Mobius strip and something like that. And one of the questions about computing Euler characteristic of a Mobius strip, right? So the Euler characteristic of a Mobius strip, and the point is that you can, or the Euler number, okay, so, or number, right? So I sometimes say Euler characteristic, I sometimes say number. So Euler characteristic of a Mobius strip, this was one of the questions. And this, I sort of explained that you can do it by just trying to draw an embedded graph. And the rule is for surfaces with boundary, right, which are not closed, the rule is that the boundary edge, if there are more than one, all of them should be edges of the graph. Okay, so that was the rule. So if you try to do it for a Mobius strip, so here's my Mobius strip again, sort of this topological representation. Let's do the graph where, okay, so these guys, so I'm going to look at the edges where, okay, so this boundary, all these should be part of the edges. Okay, so I'm going to draw it red and green, but these should be part of the edges. Now let's count how many vertices and edges there are in this one, in what I've drawn, right? So okay, so maybe I do orange for the vertices these times. So these are, if you forget about the identifications, then this is what you see. But remember, we are identifying the various things in this when we make this Mobius strip, right? This green side together with these orange, this orange vertex and that orange vertex are identified with this green side and this orange vertex and that orange vertex, right? And so which vertex gets identified to which? Well, if I, let me sort of use some other color to circle. So this guy, this circled guy will be identified with this, and then when you glue the other one, so this one will be identified with that, right? So after identification, there are two vertices, okay? So the number of vertices is equal to 2 after identification, okay? What are the number of edges? Well, the number of edges, so again, you have to think of after identification. So initially we see, so 4, right? So the 4 sides of this rectangle. right? So you have sort of 1, 2, 3, 4, but 2 and 4 are identified, right? So you identify, you're gluing them. So you see that the number of edges has to be 3, okay? And the number of regions or faces, whatever you want to call it, is 1, right? Because there's this inside of this Mobius strip, which is a single face. When you look at this graph on the Mobius strip, it bounds this face. It's staring at you. It's this region which is a sort of a valid region, right? It's just lying flat on the plane, and sort of no holes and things like that. So that's just 1. So if you compute the Euler number, the formula, the alternating sum, you would get, so the Euler number is usually denoted as a chi, okay, and that's 0. Okay, so this Euler characteristic, so this answers the question, one of the questions which we had, which is 0. Yes.
So you wrote the number of edges is 3.
Yeah.
I know that the number of edges for a Mobius is 1, but
No,
here
so
we
no, it's the number of edges of a graph that you're building, right? So the graph that I've built is uses these edges that we see in this picture. There are 4 edges in the picture, right? But after identification, there are 3. Okay, so the top and the bottom edges are not identified in any way, right? So they are between these vertices. So to compute the Euler characteristic, you have to put a graph. You have to embed a graph and then count the number of vertices and edges and so on. And the complement of the graph should be valid regions. Okay, that's the rule. Okay, that's how you compute an Euler characteristic. So you have to put a graph and then do it. Okay, so without putting a graph, you can't compute the Euler characteristic, right?
Sir, won't the edge 1 and 3 be the same? Because it's the same, right? Like if I run across 1, I'll come to 3.
No, we are not identifying. There's no identification, right? So there is and we are introducing vertices at the 2 ends, right? So there is this yellow circled vertex, and there is this purple vertex. So now we have kind of, this boundary edge, which was 1, you're right, it was a 1 connected thing. Now we split it into 2 because we've added this vertex.
So basically on that edge there are 2 vertices, and that's
right. Yeah, so you can try to visualize what happened, what this graph looks like in the original picture. Okay, so in this, on a real Mobius strip, how it looks like. You should translate this topological picture there, and there you would be able to see this better. Okay, all right. So there's other question that I wanted to sort of discuss this.
And this 2 and 4, you're drawing that edge, right? Like we can also like chuck that edge, right? Like we don't need that edge, right?
No, it has to be a connected graph. Okay, so yeah. So the other thing that we want to so I mentioned in the first thing, when you're computing an Euler characteristic, you embed a graph. It needs to be connected.
Okay? Why is it not connected if it's not? It's still connected, right? The 2 dots, like the 2 vertices are still connected, right? Even without the green color.
Yes. So it's still connected. That's right. Okay, fine. But its complement has to be valid regions, right? Which are not, so these are regions which are flat. Okay, so these are not simply connected, doesn't have any holes. So if you don't do this, then the complement.
The regions will be 0. Wait, regions will be.
Yeah, so it's kind of harder to see what the region is, right? So, but it turns out it's not it's not going to be something which is something which is flat and sort of
will I still get the Euler characteristic if I consider just 2 vertices on one
edge? I don't think so. I think you do need to make sure that the region is something which is sort of simply connected. Okay, so this region needs to be flat. Okay, but you can play around and try to see what you get. Okay, so the other thing is there was this question about identifying what surface. Okay, before that there was a question. Somebody asked an important question, which is, why is a Mobius strip non-orientable?